is just decide on a different covariance function. So if we of it as well, if we fancy it. Here to 2020, there's now we could add, in order so the bias term would allow these lines to be no longer centered. But we could combine it with other parts. So the add that on to this some underlying sort of non-linearity, but they've got might be suitable for something like financial data. It's about doing it with I'm just going to reset it so that we're looking at predictions for this exponentiated quadratic, which we said has an origin as a basis. This exponentiated quadratic has several things together in the same model. You kind of have to go to because you can't represent each of those covariances in those represent these things as a model. Now, of course, than the Gaussian process, but from a model. That's the sort of big advantage of these things. Let me just down at 0. Motion and the smooth thing from the exponentiated quadratic. The linear term having an effect of these things. If I multiplied this by, say, so the length scale, sorry, the length scales. So now we're seeing dominating terms on there as well. There must be some underlying linear terms. multiply this by 16, so it's got a standard deviation of 4. Can vary as well how much linear. And of course, when you look differentiated quadratic. Okay, so I mean that's remember the form of all these covariances. So in one comma without necessarily having to remember their functional form. Now, but there are some other covariances models, and I don't want to have etc. So I was just getting down to the sampling bit. So if I wanted Brownian 1 comma v yeah, so then I get the Brownian motion. That's going to be interesting. It's a valid covariance. I've not tried it before, is x comma x prime. So that's the form of that covariance function. As well. When you look at the function, it kind of makes sense what it's doing. It's suppressing an x prime times x prime. Near the origin, x and x prime are both 0. So what it would have been before. The RBF by the Brownian motion. Okay, so you can see that there's various things. But you don't just have to sample from them. Having done what you've done, I'm not sure that I remember, but I think is it very highly smooth, or is it non-smooth, or somewhere in between? smooth and non-smooth? Done? The Matern 5-2, because it's got this sort of little roughness. Yeah, it could be. So Maurizio is asking, is it the sum of two lengths? One length, what do you want the length scale and the variances to be?
Yeah.
It's like doing magic. You kind of still get the sense it's smooth. It's an infinite mixture of these. See if we don't have of these exponentiated quadratics. So it's like infinite of them being all added together, and it just. If I've got a kernel function that adding these with different length scales, you sort of but since it's an infinite sum of covariances, it's infinitely differentiable, but it has all these length scales. You see is more characteristic, you know. In the Fourier spectrum, allowing heavier tails. Yeah. Okay, good, well done. Right, let's try and run that. Rational. See. Now alpha, I think, is the other parameter. I can't remember how alpha. .1. This gives a parameter of the gamma prior. I think, if I recall correctly, when I changed the power. Differentiated quadratic covariance, because this gamma function is in the Matern, because we're allowing a quadratic, because we're seeing a combination of an infinite sum. So that's the rational quadratic covariance. So I think that's actually a Matern 3/2, though. How about this one? Any ideas for this one? King Brownian, and this one here as well. So I think if I remember correctly, and I may not remember correctly, this one is actually a the Ornstein-Uhlenbeck process. One of them is. I can't remember if it's that one or not. So the Ornstein-Uhlenbeck process is like a Brownian motion, but occurring. Brownian motion isn't stationary, because if you leave it over time, the pollen particle just moves off wherever it likes, goes on a random walk, and, well, we can see from the covariance function what the marginal variance is. So it's the min of x, comma x prime. So along the diagonal, the marginal variance is, of course, the min of x and x prime. It's just x. So the marginal variance goes up like square root, the marginal standard deviation goes up like square root of x. So you get this sort of process that when you look at it, if you look at Brownian motion, this is the effect of a random walk, you get a process that is going up over time in standard deviation at the square root of time. Now, this one here, the Ornstein-Uhlenbeck, is actually Brownian motion, but occurring in a sort of field. The way I like to think about the field, it's I like to think about it occurring in a parabolic gutter. So you've got the pollen starts in here, he's getting bounced around left and right, but he's being pulled down, and as he goes uphill, he'll go back down a hill. So it's a random walk, but with some centering force. So that actually leads to a stationary covariance function, and it's the SDE underlying it. It has this a decay term in the stochastic differential equation, and the decay term gives you this Ornstein-Uhlenbeck, which I never know if I'm saying correctly. Ornstein. Oh dear. Should be there somewhere. It might be called exponential because it's got this exponential form. I prefer to call it the OU, but it's called exponential in this case. The Ornstein-Uhlenbeck process. And if we take a look at that, let's increase that length scale back again to 1. Now it's like a Brownian motion, but it's staying stationary, yeah? It doesn't keep going off like that, and it doesn't start at 0. It's like a Brownian motion triggered here, and sitting in this tube, so it sort of bounces back down. Now, it's not only got that interpretation, it also has a spectral interpretation. This is the same covariance that has this spectral interpretation of being the result of filtering in Fourier space with... Does anyone know what the inverse Fourier transform is of the exponential, or the Fourier transform of the exponential? No. I thought there were electrical engineers in the audience. I would never know this. But I thought electrical engineers might. That's the filter. It's applied in Fourier space. So it's this heavy-tailed filter. So we get the Gaussian by doing a Gaussian filter, but this is a very heavy-tailed filter. It's actually a Cauchy distribution. So it's allowing very, very high frequencies. And it's a part of the Matern class of covariances again, because this is a particular variant of the student T. But it also has other interpretations of this stochastic differential equation. So non-differentiable, but continuous paths. Now, what else have we got down here? How about this one? What's going on there? We haven't come across this covariance. Can anyone have a guess what this covariance is doing? Periodic. Something periodic, yeah. So this is actually periodic covariance. There's a few different ways of building periodic covariances. One is to use that trick of filters in Fourier space. So you can say, okay, I've got a filter in Fourier space, but I believe things are periodic. So I'll make my filter, it's got to be symmetric to avoid the centered around some omega in Fourier space. And what you get out of this covariance is actually, well, if you put a delta function on omega, it turns out that cosine omega x minus x prime, of course, because the Fourier transform of this is cosine, turns out that this guy is a valid covariance. So cosine on its own. But you're putting all your maths, you're saying that there's only that frequency. So the model has no chance to do any inference, basically, so that's an odd covariance. If you allow it to spread out, you get this product of a cosine and an exponentiated quadratic, where this width here is 1 over the length scale of the quadratic here. So this sort of says, imagine if you make that broader, this starts becoming peakier and starts removing the cosine. So that's one way of getting periodic. That's not how this one's done, actually. This one's done by, if memory serves me right, building an exponentiated quadratic covariance function in a space that forces it to be periodic, so like in a sine-cosine space. I think it's called, in GPy, I believe it's called RBF periodic. Oh, let's have a look. Periodic. Oh, maybe it's not even. No, maybe we don't have that one implemented. It's the easiest one, so I'm surprised we don't. But there's the Matern 5.2 periodic. So it may be the Matern 5.2 periodic. And the period is obviously larger than anything we're looking at. So let's have a look at the. Let's look at the help, so we can try and check the period. Period, the period. Yep, it's called period. Okay, so I'm going to put that in as the period. So period equals 0.3. Is that small enough? Length scale equals 0.1. Let's see if that works. Okay, look at that. Yeah? A bunch of different periodic functions. Now they're not pure sinusoids or anything. Look, there's a little corruption you can see there, but they're all periodic. Now, what if you weren't sure about that periodic function? What if you sort of thought, oh, maybe things are periodic on a yearly basis? Yeah? What could I do to sort of soften this periodic function? Has anyone got any ideas? So maybe things aren't sort of totally periodic. They're sort of pseudo-periodic. So when we could add another term to it, that's one thing, yeah? But another thing we could do, we could allow the period to soften as the years go on by multiplying by an RBF, or whatever we want to multiply by. 1, what should we say, length scale equals 0.3. Now, if you do this, those functions will be sort of pseudo-periodic. So we've got to pick out. Let's try and plot fewer because we can't quite see in the jumble about this pseudo-periodicity. So let's plot 1 or 2. Let's plot 2. So they've got some periodic nature which I can't quite pick out. Have I done that right? Maybe I need a longer length scale. If I make that length scale a bit longer, let's make it 1. That should keep the periodic nature for longer. There we go. That's better, isn't it? Yeah? So some sort of pseudo-periodicity. Nice, eh? So you can get these functions that they're going up and down together, vaguely periodic, but they don't share exactly the same shape. Their shape evolves over time. And the time scale over which their shape's evolving is determined by the length scale over this RBF. I had it too short earlier. When I made it too short, then we couldn't really see the periodicity anymore because the periodicity was evolving more quickly than we could visualize it. So, but if I make it too long, we'll start seeing that the periodicity stays pretty much the same. So that's really cool. You've got the ability to look at a function. So let's think about students walking down the road or something, right? That's probably a periodic thing. They've got lectures. But things happen like term ends and stuff like that. So that's a discrete thing, so it's not a great example. But if that periodic function was evolving over time, we can handle it with a covariance function like this. What else? Should we have a little, let's see in the help if there's functions, covariance functions that I haven't talked about yet.
If you, for instance, had like a reason to believe that things should behave in some sort of periodic, but they can also change for other random things, like that you would add instead of multiply.
You could, yeah. So you could have a periodic if you thought there was an additive effect. So if you thought it was solidly underlying periodic, but then there was some distortion of the periodicity by some other operating process, you could just add in another covariance function. Or if you thought, for example, we might think that there's two periodic functions, one's going on a daily basis and one's going on like an hourly basis, and they're not being dispersed at the same rate. So maybe one of those stays much longer. So we might be able to multiply one of those by one RBF and the other by another RBF, and then you would be trying to pick out a signal that is an hourly varying evolving periodic signal and a separate daily evolving periodic signal. You get quite complicated things out by doing things like this. Yeah? Sorry, I was just checking here, wasn't I? So these things here, ODE1, ODE-UY, I kind of hope to show you, they're the results of latent force models. So they're the results of deriving differential equations with Gaussian processes, which is something I'll talk about later today. The Gibbs covariance function is one where the length scale varies across the inputs. MLP you've seen. Polynomial. Ooh, evil polynomial. The guys didn't even implement this. I implemented it just for the sake of demos like this. Yeah, so it's there. This is the... Oh. No, I think maybe it's not called degree. So I'm sort of the code's kind of based a bit on our old MATLAB code, and it's just called D. Oh no, is it not? Unexpected. Come on, come on. Degree? Yeah, it was degree. What have I done wrong? Oh, look, we found a bug. Potentially. Okay. So there's that looks like a bug. So polynomial's not working, I guess because we never use it. So that's something. Okay, so what do you do when you find a bug in GPy? Well, so you go to the GPy GitHub and you raise an issue in GPy because it's BSD open source. So let's see. Oh, I'd have to sign in. So you can raise issues. You can join here, new issue. Once it's signed in, I can say new issue, polynomial covariance not working. Yeah, of course, if you were raising an issue, we would expect more detail than that. Yeah, so I've raised an issue there, so I remember to check that when I get back. So GPy is hosted on GitHub. GitHub provides all the facilities for checking in code. You can fork it. You can do things with it as you like. So that was good. That was a demonstration of software in practice. Okay, right. So what I think we'll do now is we'll take a break for just maybe 10 minutes, and then we'll come back. And what I want to do next is these covariance functions have been over sort of one-dimensional outputs over time. And what I'm going to show you next is what you can do if, for example, you're trying to build covariances over a discrete number of objects. So if I want to model your heart rates in this room over time, okay? So your heart rates are evolving over time. They're mostly evolving independently. But if I say something very exciting, like if I show you a really nice covariance matrix, all your heart rates quicken up, yeah? And so there's some commonality to your heart rates, but there's some separation to your heart rates. Now, what if we wanted to do a joint multi-regression over all your heart rates? So what I'll show you afterwards is how we do that. But we're going to start by showing, first of all, the Kalman filter, how we can derive the Kalman filter as a Gaussian process, because it turns out to be a multivariate Gaussian process. One way of doing that would be to model your hearts with a Kalman filter, right? I could have a Kalman filter, which is some sort of latent Gaussian process with emergent properties, and then that Kalman filter might be how exciting is what's on the slides, plus some corruption. Yeah, and then I get a joint correlated thing of what's going on with your heart rates. So we'll start by deriving the Kalman filter as a Gaussian process, deriving its covariance function, and then once we've seen the form of its covariance function, which I don't know if people normally write down as a covariance function, I'd not seen it before, I sort of had to derive it, then we'll say, what happens if we use non-Markov processes in the latent function in the Gaussian process? And then we get these generic classes of multi-output Gaussian processes that Maurizio is the world's leading expert on, because he wrote the authoritative review of this area. And so I'll use that to lead into these multi-output Gaussian processes and show you how you can extend what you've been doing so far to multiple outputs. And then we've got an example in the lab class where we're going to look at the Olympic sprint data from 1896 to 2012 for all sprint events, 100 meters, 200 meters, 400 meters, men and women. And we'll make a joint prediction over all these things. And what that's going to enable us to do is answer questions like, how fast would the women have run the 400 meters in 1904 if they had been allowed to run it, because they weren't allowed to run it. But if we look at the structure of how the women are evolving with the men, and how the 400 meters is evolving with the 100 meters, we've got some 100 meters data, maybe we can pick that out and make a back prediction about what's going on. It's actually an extrapolation of the data in some sense. And we'll see there's some issues there that we can maybe, we get out what we put in again. You know, prediction is data plus model. And what we put into the model, how we vary the model, will affect that prediction. So that's what we'll do in the lab after we've done the multi-output session. Okay, so let's break now for 10 minutes. So back here at 20 to 10.